Dear students, today we are going to learn about the nomenclature of organometallic compounds and 18 electron rule. 18 electron rule is used to predict the stability of organometallic compound, an important concept. Now we are move into our video lecture. As we know, in the case of coordination complexes, metal can bind with the ligands through different atoms. For example, here platinum is the metal. It binds with chlorine and an alkene. So there are two different atoms present in this particular compound, which is known as Z salt. Another one example is TEPS reagent. Here there are two metals are present. One is titanium, another one is aluminium. Titanium is bonded with chlorine, a methylene bridge, that is CH2, and it is also bonded with two cyclopentadienyl ring. So the coordination number of titanium is of course 4, but there are 3 different ligands are bonded with the titanium. In the case of nomenclature of organometallic compounds, we use a word called hapticity. Hapticity is derived from a Greek word which means fasten. So fasten means when you are driving a car, you put a seat belt. It means to fix or link or join. That is the meaning of the word hapticity. So based on the hapticity, we are going to classify this organometallic compounds. So how can we define hapticity? It is a simple definition. Just we calculate the number of carbon atoms of an organic moiety linked to the metal. This is very important. The carbon atom of organic moiety linked to the metal is called hapticity. Suppose if only one carbon is linked to the metal, then it is called as monohapto. If there are two carbon atoms are linked, then we call it as dihapto. If there are 3 carbon atoms, then it is called as terhapto. So hapticity or hapto can be represented by H1 or eta power 1. That is the representation we use in the case of hapticity. In this slide we have 2 examples to show what is hapticity. In this example we have palladium as a metal ion which is bonded to 4 different atoms. One is phosphorus, one is nitrogen, another one is chlorine, along with a carbon, an organic moiety, an alkene like compound. So 4 different atoms. So as per our definition, hapticity means the number of carbon atoms of an organic moiety linked with the metal. Therefore, in this compound, palladium is bonded with only one carbon of the organic moiety. Therefore, we call this as H1 or eta 1. So eta 1 means only one carbon is attached with the palladium. Now we come to the second example. In this case, pentacarbonyl manganese reacted with propenyl chloride to form an organometallic compound which has 5 carbon monoxide ligand attached with it along with the propene ligand. So normally you have to look into the organic moiety. So in this case the organic moiety is the propene ligand. Here the propene ligand is attached with manganese with only one carbon atom. So here also we have the hapticity as 1. Do not count all the 6 carbon atoms and say hapticity is 6. You just count the number of carbon atoms of the organic moiety. You do not count with the CO. So that is very important. So what happens next is very interesting. When you heat this compound, one of the carbon monoxide ligand is left from the compound and you get a different organometallic compound. And here you see there are only 4 carbon monoxide left in the compound, and the propene ligand is now, it is in like a modified ligand, that is like an allyl ligand. So here it is a V-shaped structure and a curve. So the V-shaped structure shows that there are 3 carbon atoms, and the manganese metal, that is the manganese atom, is bonded with 3 of the carbon atoms, not with the single carbon atom in the earlier organometallic compound, but here the manganese is linked with 3 carbon atoms simultaneously. That's why it is represented as like a curve. So here, since there are 3 carbon atoms is directly bonded with manganese, the hapticity is eta 3. So now you can differentiate about eta 1 and eta 3. Here I am going to give you some more examples. This compound is called as dibenzene chromium. You see, chromium is in between 2 benzene rings. We all know that benzene has 6 carbon atoms, and the chromium is bonded into the ring. That means that all the 6 carbon atoms of that benzene ring is linked with chromium. Therefore, you see the structure is Cr, hapticity 6, eta 6 benzene. So there are 2 benzene rings are present. Therefore, the formula Cr eta 6 C6H6 twice. So eta 6 shows that there are 6 carbon atoms in the benzene ring, and all the 6 carbon atoms are joined with chromium. And you have encountered about ferrozene in our previous class. Here is the structure of ferrozene. Here there are 2 cyclopentadienyl ring present, and iron is present in between the 2 cyclopentadienyl ring. In the case of ferrozene, the hapticity is 5, that is eta 5, because all the 5 carbons of the cyclopentadienyl ring is attached with the iron. Here I am going to I have given some more examples to explain about hapticity. So let us look one by one. If you see the first example, that is the number of bonding position is 1, and formula is eta 1 C5H5. So in all the 3 cases the same ligand is present, but in the first example the cyclopentadiene ring is bonded through only 1 carbon atom with the metal. So that M is directly bonded with only 1 carbon atom. So the hapticity is 1, that is eta 1. Now come to the second example. Hapticity is 3. You see the bonding is little bit different. As we saw earlier in the case of propenyl and allyl, here the bonding position, that is a V-shaped position, that shows there are 3 carbon atoms and a curve, and that curve is directly attached to the metal. Therefore 3 carbon atoms of the cyclopentadiene ring is attached to the metal. Therefore the hapticity is 3. And in the final example the hapticity is 5. And now look at the bonding position. All the 5 carbon atoms of the cyclopentadienyl ring is attached with the metal, and that's why there is a ring is placed inside the cyclopentadienyl system, and that ring is directly attached to the metal. That indicates all the carbon atom of cyclopentadiene, that is 5 carbon atoms, are bonded with metal. So from these three examples you can clearly understood about the concept of hapticity. In this slide, how we can name a simple organometallic compound. This is the rule, that is, it can be written in one word. The name of the organic group is followed by the name of the metal. That is the very basic rule to name an organometallic compound. Here are some of the examples. So if the compound is pH, Hg, pH, so as per our rule, the organic compound name comes first, therefore diphenyl mercury is the name. The next compound is hexaphenyl disaline. Since there are 6 benzene ring attached with that silicon, we call this as hexaphenyl disilane. Another one name is trimethyl tin acetate. Another one is butyl lithium. So these are the examples of how to name a very simple organometallic compounds. And in this slide we are going to learn how can we name if some ligands are present as bridging ligands. So bridging ligands can be designated by the prefix mu followed by a subscript. So that subscript indicates the number of metal atoms bridged. Here are some of the examples. If there are no bridging ligands, then it should be terminal. The formula should be just, if CO is the ligand, then the formula should be CO. If there are 2 bridging atoms are present, then it can be written as mu2 CO. If there are 3 atoms are bridged, then mu3 CO. Here are the examples. The first one is terminal carbon. No bridging metal atoms are present. The next one is mu2, and you see there are 2 metal atoms, and in between the 2 metal atoms that CO is present, therefore we call it as mu2. And in the next case, that is mu3, and there are 3 metal atoms, and that CO is present between the 3 metal atoms, and we call this as mu3. Here is another type of classification. One is called as homoleptic and another one is called as heteroleptic. In the first case, that is with the iridium, there are 3 different kinds of ligands present, and that those 3 ligands are indicated by different colors. So if there are different kinds of ligands are present in an organometallic compound, then it is called as heteroleptic. And below that iridium compound, there are 2 different organometallic compounds. One is dibenzene chromium and another one is hexamethyl tungsten. So in those compounds, same type of ligands are present, and they are known as homoleptic organometallic compounds. This is another one type of classification. So here are some of the references you have to look to know about more examples based on the nomenclature, and I have taken some of the examples from these books. Now we are going to study about or discuss about 18 electron rule, an important concept in the case of organometallic compounds. So this rule is used to predict the stable organometallic compounds, and it was first proposed by Irving, an American chemist, in the year 1921. So we all know about octet rule, which is used to predict the stability of main group elements that we have studied in our first year itself. So 18 electron rule is very similar to that octet rule, and this rule is used to predict the stability of organometallic compounds. So that's all. Octet rule is used to predict the stability of main group elements. Similarly, 18 electron rule is used to predict the stability of organometallic compounds. Both are very similar. Now let us look into a bit detail about the 18 electron rule and why it is called as 18 electron rule. So usually organometallic compounds can be formed only by transition metals, Tm. So the central transition metal can accommodate electrons in their s orbital, p orbital and d orbital. So a maximum of 18 electrons can be accommodated in a transition metal. That how 18 electrons can be added, that I show in the split up. Now a transition metal can add electrons from ligands in addition to its valence electrons to a tally of 18. So if an organometallic compound can add to a tally of 18 electron, then it should be very stable, and it is also known as effective atomic number rule. Here is a summary of the 18 electron rule, or EAN, which is known as effective atomic number rule. So it works well only for the d block elements, and it is also work best for compounds with low oxidation state. So ligands which are very good sigma donors and pi acceptors, and those type of compounds obey this rule to very perfect. So complexes which contain a combination of sigma donors and pi acceptors conform to this rule, and I have given some examples to this. Compounds which obey this rule are kinetically inert or to a substitution reactions. Exceptions to the rule occur at the two ends of the transition series, where Nd, n+1s and n+1p valence electrons are less well matched in energy. So if the energy of orbitals are not well matched, then this rule will not work out. So these are the summary about EAN rule. So now how we are going to convert the electron? Here is the calculation, very simple. The number of valence electron of the metal is added with the number of electrons donated by the ligand. So if it comes to a tally of 18, then that organometallic compound is very stable. So what we are going to do is, we have to count the valence electron of the metal and adds with the electron donated by the ligand. So as I said earlier, if the total is 18, then such complexes or compounds are stable. There are two methods available to count or to predict the EAN rule. First method is oxidation state method, also called as ionic method. The second method is neutral atom method, which is also known as covalent method. And in this slide, how we are going to count the electrons in the case of 18 electron rule in oxidation state method. Neutral ligands, for example ammonia, are considered as neutral, and it can donate 2 electrons to the metal. So each neutral ligand can donate 2 electrons. Methyl chlorine like ligands, they can be viewed as anions, CH3 minus, Cl minus, and not as neutral radicals. And H is also viewed as H minus, not H. So after removal of the ligands, the metal is assigned a formal charge in the case of oxidation state method. So let us go into the oxidation state method first, and how we are going to calculate the 18 electron rule. Then we see about the neutral electron method. Here there is a tabular column which shows the ligands along with the electron donation capacity of ligands in neutral atom method and oxidation state method. So let us see one by one. First we see about carbonyl. So in the case of oxidation state method, it contributes 2 electrons, and there are no formal charge in the case of carbonyl, which is just a neutral ligand. Similarly, then phosphine, it also contributes 2 electrons and no formal charge. And now I come to MuCO, which is shaded in the pink color. So that carbonyl is also donates 2 electrons with no formal charge. Then I come to the next column, that is halogens. So in the case of halogens, it contributes 2 electrons, but the formal charge is -1, as we know earlier. Similarly, alkyl, that is CH3, C2H5, whatever it may be, it also contributes 2 electrons and the formal charge of -1. Aryl, similarly 2 electrons with -1 formal charge. Then I come bit down, mu H, which is shaded in purple, that is purple color. It also donates 2 electron with the formal charge of -1. So various types of ligands along with the electron contribution is given in this table. You have to memorize some of the ligands, and then only you can calculate the EAN rule. Here we are going to see about some of the examples of the calculation of 18 electron rule. First one is CrCO6. So there are 6 carbon monoxide ligand which are neutral. So each carbon monoxide ligand contributes 2 electron, therefore 6 carbon monoxide contributes 12 electron. The valence electron in the case of chromium is 6. The electronic configuration is 4s1 3d5. Therefore 6 valence electrons are present in chromium. So on adding 6 plus 12 gives 18. Therefore this complex or this compound is very stable. Then we come to the next example. There are FeCO5. So 8 valence electrons are present in the case of iron. The electronic configuration 4s2 3d6, therefore 8 valence electron, and 5 carbon monoxide ligands. So each carbon monoxide donates 2 electrons, so the total is 18. Again a stable compound. The next compound is NiCO4. So nickel has a valence electrons of 10, and there are 4 carbon monoxide ligands, contributes 8 electrons. Here also the tally is 18. Therefore all the 3 compounds obey 18 electron rule, so and hence they are stable. Now we are going to see about some bit complicated examples. So the first one is cobaltocene, similar to ferrocene. This is cobaltocene, and then a titanium compound, rhodium compound, and then is a tungsten compound. And we are going to calculate the 18 electron rule based on oxidation state method. Here is the calculation. So each cyclopentadienyl ring contributes 6 electrons, so tally of 6 each cyclopentadienyl ring contributes 6 electrons. 2 cyclopentadienyl rings are present, therefore 12 electrons can be donated to cobalt. So each cyclopentadienyl has a formal charge of -1. 2 cyclopentadienyl, therefore 2 minus, and the cobalt metal occur CO2 plus charge. So cobalt has a valence electrons of 9 electrons. Since the charge is now 2 plus, it now has only 7 electrons. So the total is now 19 electrons. Next we move on to titanium compound. So in the case of titanium, there are 2 cyclopentadienyl ring with the formal charge of -1 and 2 chlorine ligand with the formal charge of -1. So totally 4 minus formal charge, and hence titanium occurs titanium plus 4. So there are no electrons present in titanium, so 0 electrons. 2 Cl minus contributes 4 electrons, 2 Cp minus contributes 12 electrons, and 12 is 16 electrons. And the next compound is rhodium. So in the case of rhodium, only the chlorine is an anion. Triphenyl phosphine is a neutral ligand. So 3 ppH3 donates 6 electrons. That 1 Cl minus donates 2 electrons, and rhodium oxidation state becomes RH plus 1, which has 8 electrons or 8 valence electron, and the tally is again 16 electron. And the final example, it is very simple. All the 6 carbon monoxide are neutral, and the tungsten has a valence state of 6 valence electron. That means the oxidation state is 0, since there are no formal charge present in the case of carbon monoxide. So the valence electrons are 6 carbon monoxide donates 12 electrons, and 18 electrons are present in that final compound, and that is very stable. So all the above 3 compounds violate, that means it does not match with the 18 electron rule. So that those compounds are unstable.